Okay, so let's first review a couple of things we did on Monday about taking measurements, kind of like what we just did on the board, and then we'll go into looking at conversions of measurements, and then go back to the lab. Well, one thing a lot of people had questions about in lab, I think good questions, and it was really good that you caught this, is this instrument called a burette. The burette was the thing that was hanging on the plant. Anybody remember that? You remember what was weird about it? I know at least a few people said something about it.
You know exactly if you're measuring the volume in it or...
Yeah, it was hard to tell exactly what you were measuring because it was upside down. The scale was upside down. The 0 was at the top and the 25 was at the bottom. So it looked, if we imagine kind of the middle of it, it was like this. Something like that. Whoops, except opposite. Switch that again. So it counted up instead of counting down. So if your liquid level was, let's say, here, some of you had the question, well, how do I read that? Do I just read what the value is, or am I supposed to subtract it from 25? And the answer is, you just read it. It's listed that way for a reason. The reason is that this is not actually meant to contain a certain amount of liquid. It's meant to dispense liquid. And you'll find lots of different devices for dispensing liquid. Sometimes, like in chemistry, we have these burettes, but if you look at hospitals or other places like that, you have things like, I don't know, what are the things they have in the pharmacy? The bags, but then the ones that you can actually measure the amount that's coming out to. Yeah, and they have similar markings. And then you have syringes, which can go both ways. But again, with a syringe, you're focused on what you get out, not what you're taking in generally. So same idea. So let's take this as an example, and how would we read that? What would you call that value? So everybody write something down, what you would call that value in milliliters. Hold on, we'll give everybody a chance. Everybody, and I want you to commit to this answer as though you're being quizzed or examined or something. So actually write it down. The reason for that is we like to fool ourselves into thinking that we know more than we do. I don't know if you've ever noticed this, but sometimes somebody asks you a question like this, and you say, okay, I think it's about this, and then it turns out that you're wrong, but because you didn't really write anything down, you say, oh yeah, well, I knew it, I just wasn't thinking right, or something like that. You sort of fool yourself into it. If you really write it down, then you have to confront the fact that you really didn't get this right. And that shows you that you have to kind of think about it a little bit more. So everybody write something down, what you think this measurement might be. And again, we're just starting this stuff, so I'm not saying you have to be right now, but it's good to know if you are right or not. So everybody got something? Got some numbers down? Does anybody want to share what they got?
6.59.
6.59. Okay, somebody get something different? 6.39. Did you have something different? Okay. Mm-hmm.
Okay. 6.49.
Okay. Yes.
7.69.
All right, that's a good range. Do you think they're all correct? Probably not, right? Seeing as they're not the same. Could multiple of these be correct? A couple of the ones that are really close could be correct. Okay, so let's look at it. First thing you have to look at is your scale, your measurement device. And sometimes it's going to be weird, like this one's a little different from what we're used to. But they still work in the same basic way. You have certain numbers that go up in a particular direction. So would you say that this amount of liquid, or this particular liquid level, which I know it can be hard to see from where you're sitting, so I'll draw a little line. At that point there, would you say that that is greater than 5 or greater than 6? That seems to be the discrepancy here. And how do you know?
Well, if it's greater than 6, it would obviously go below like where the 6 mark is.
Yeah, that's how you can tell. So yes, this liquid level is above the 6, as in it's higher than the 6. But on the scale, it's between the 5 and the 6, right? Everybody see that? So if it's between the 5 and the 6, you gonna? Oh, okay. I just had a second. Because it's between the 5 and the 6, we know it has to be 5 point something. If it's 6 point something, that would mean that it's between what? 6 and 7. So yes, at first glance, it looks like it should be 6 point something because the liquid level is above the 6. But you have to look at the scale to be sure, right, to see where it is. And even though this is kind of weird with this one, on a ruler, this actually happens all the time because we're often measuring things in a weird location where sometimes we're not sure which side we're looking at on the ruler. So it's always good to look at the surrounding numbers and say, okay, is this thing between 5 and 6, or is it between 6 and 7? And that'll give us the right answer. So let's, let's say that we're gonna say for sure it is between 5 and 6, so it's going to be one of those 3. How do we get the rest of it then? What's the next thing we look for? Count. What do you mean count the digits?
See where the lowest part of like the steep is, and try and get it to the closest like digit between the 5, more.
Yeah.
5.5 and 6.
So we have to figure out what is the next thing that it's in between, right? Like, that's what you're saying, right? The next digit?
Yeah.
Yeah. So we're going to count these out. 1, 2, 3, 4, 6, 7. That line then is between the 6 and the 7, right? So that means that our next digit must be 6. So it can't be 7 because that would be beyond the 7. And it can't be 5 because that would be below the 6. We know it's above the 6. So what comes next? Are we done, or should we have another digit in there? Everybody picked another digit. How did you know that? Just guessing? Okay. Is there a way we can figure that out without just guessing? Yeah. This is the. Did you want? Go ahead.
Well, because it's not on an exact number, so there's actually like accurate.
Right. We've exhausted all our exact numbers because we no longer have a little tick mark, have a little mark telling us, well, this is definitely greater than this or definitely less than this. So this means that we're now in guess land. We have to make a guess. And once you're in guess land, you're done. That's your last digit. You have to make that guess. You have to put that digit down there, but you can't write down any more numbers after that. So depending on how you see this, you call it whatever you like. And so 6.2, 6.1, these are probably the better answers here. Even you could go up to 6.3 or 6.4. Those would also be okay. So that's the proper way to make that measurement. Now, how many significant figures are in this measurement? 3, right? All 3 of those numbers are significant. These two are certain, and this one is uncertain, but they are all significant. Yeah.
What are we measuring in this? Liquid.
Yeah.
Okay. In my understanding, even though I got the answer wrong, like I feel like it was a guesswork. I don't still understand why I got it right.
Mm-hmm.
But I feel that if you have a liquid in a container and you put the ruler or the measurement for upside down,
Yeah.
your measurement you have to start reading from down, not what you're being covered by a liquid.
That's right. That's right. And that's why the graduated cylinders, the tubes that we pour the liquid in, always start 0 at the bottom. This is a special thing. This is called a burette, and it is not meant to measure a certain amount of liquid. It is meant to dispense a certain amount of liquid. So the way this works is you might come up to the burette, and it is now at 5.63. Then you let a bunch come out until it's at 2.63. You have just dispensed 3.00 milliliters. Okay, so it's a different kind of apparatus. But because you still got it right, that's great, because no matter what kind of device you're using, you need to use the scale on the device. In other words, if this were meant to hold liquid, like you said, the scale would start 0 at the bottom and go up from there. But because it's meant for a different purpose, we have to use its scale and not be too tricky about it and just, okay, this is the scale I see, this is the scale I'm going to read, that's it. But you're right. I mean, if that were holding liquid, that wouldn't make sense. Okay. Next thing to review, something we'll use a lot this semester. Scientific notation. I'm going to apologize. This chapter, I think, even in the scheme of this class, is particularly dry. I mean, we're just making measurements and we're dealing with certain types of numbers, and I'm sorry about that. It will be more exciting, I promise. Just bear with us while we review some of this kind of stuff, okay? If you need to take a little nap because you're bored, I understand. It's late. You probably worked all day. It's all right. That's why we're recording the videos. All right. Who knows anything about scientific notation? Have you used this before? What does it look like? What does scientific notation look like? Exponents? All right. What's it for?
Shorten it down. Make it smaller, make a large number.
Yeah, it ends up being easier to write really big numbers. Let's take a small example to start with. 1,000. Now 1,000 is not that hard to write, and in fact the scientific notation version of 1,000 I think will be harder to write, but you'll see how it changes when we get to very big and very small numbers. So does anybody know, how do we convert a number like this to what we call scientific notation? Yeah, we use powers of 10, which is 10 multiplied by itself a certain number of times. And so 1,000 is 10 to the third power, which means 10 times 10 times 10. Now, when we get really big, it's going to be hard to say, okay, how many times does 10 have to be multiplied by itself to get this? You know, it's not a good way to think about it. So what's the shortcut here? How do you think about it? Yeah, you just count the zeros. So you see that? 10 to the 3 is a 1 with 3 zeros behind it. Okay. Let's look at a similar number then. 2,463. Now this one is a little bit trickier because we can't just drop all those numbers out. There are no zeros anymore. So the way that we write this is we say, okay, we're going to take a regular old little small number between 0 and 10, and then we're going to multiply it by that power of 3. So 2,463 in scientific notation is 2.463 times 10 to the third. How do we come up with that? Yeah.
I'm like multiplying 10
Mm-hmm.
by 2.463.
Yeah, and then again
And
and again. And that's correct. But the easier way to think about this and to always be able to convert this is to simply move that decimal place. Is that what you're going to say? So we start at the very end of the number, right here, because that's where the decimal place would be if there were decimals. And we count how many places we have to move it to just have one number left over. So we're going to move it once, twice, 3 times to just have one number left over on the left. And if we've moved it 3 times, that's 10 to the third. So 1, 2, 3 moves gives us 10 to the third.
Isn't it when it's a negative, like let's say 10 to the -3, we'll move it to the other side?
Yeah, that'll move it to the other side to make small numbers. So we'll talk about that in a minute when we finish looking at some of these big numbers. So that's correct. Why do we care about this? Other than making it easier to write large numbers. There's actually another reason. Anybody know? Yeah, that's the right idea. It's because of measurements. It's because of significant figures. Let's look at another number. Oops, keep our color scheme here. 3,500. Now let's make it 35,000. Let's convert that to scientific notation. So we're going to make a little decimal place here and figure out how many times we have to move it over. 1, 2, 3, 4. So that's going to be 3.5 times 10 to the fourth. But it could also be written a couple other ways. We could call this 3.50 times 10 to the fourth, or 3.500 times 10 to the fourth, or 3.5000 times 10 to the fourth. What's the difference in those numbers? Yeah, that's a big difference in precision, right? That's a 10 times difference in precision. There's no way to express that writing a number like this. Writing 35,000 doesn't really tell you how precise that is. Doesn't tell you if it's between 34,000 and 36,000, or 34,900 and 35,100, or you see what I'm saying? 34999 and 35001. It doesn't really tell us where the precision is in that measurement. This does. This tells us exactly where that precision is because of all the stuff we've talked about already and Monday. So when we talk about taking a measurement that ends up having a bunch of zeros in it, we often use scientific notation so that we can be very clear about the precision of our measurement. And there's no ambiguity there.
35,000.
Mm-hmm.
If you say 35 times, because the first example said 10 million moves it to the left, the zeros. So now it has 3 zeros. Why do we have to move it beyond the 0, right? After 5.
Good question. So we could call this, you're saying we could move this 3 times and call it 35 times 10 to the third, right? Yeah, and that would be okay. But the rule is, the convention is, you only have one digit before a decimal place, and then you move it. If you wrote something like this on an exam, I would have no problem with that. That would be okay. But official, proper scientific notation, you only have one digit before the decimal place. Okay. Similarly, we would say that it's not correct to write 0.35 times 10 to the fifth. That would be another way to do it, to move the decimal even more. That's also an equivalent number, but that doesn't fit the official scientific notation rules. You see what I'm saying? So we're going to stick with 1 digit out here. Okay, let's try another one. Okay. This is getting to be a pretty big number now. So this is the kind of number that it's going to make a lot more sense to write in scientific notation because we don't have to write all those zeros all the time. So see if you can convert this number to scientific notation. That same procedure, put the decimal place at the end, and see how many places you have to move it to get just one number left. And that's going to be your exponent. We're going to assume in this case that the zeros are not significant. So leave the zeros up. That's good. Maybe you want to volunteer what you got?
3.827 times 10 to the
3.827 times 10 to the 8th. Anybody get something different? Everybody got that? Okay, great. Well, that's all there is to it. Let's look now at really small numbers. Same idea, same procedure, but now we're going to look at really small numbers. Okay. So let's say we have this number. Same deal. We want to have a shorthand that allows us to account for the fact that this is a really small number without having to write all those zeros all the time. So we move the decimal place again, 1, but we're moving the other direction, 2, 3, 4, 5, 6, until we just catch one number to the left of the decimal place. Because we're going the opposite direction now, we're dividing by 10 instead of multiplying by 10. And the way that we express that mathematically is with a negative exponent. So this becomes 1.27 times 10 to the negative 1, 2, 3, 4, 5, 6. The same idea. You want to catch one number on the left of the the left of the decimal place, and you just count how many moves you have to do to make it do that. All right, let's see if you can try one going the opposite direction. This time I'm going to give you a number. In scientific notation, a small number, 3.27 times 10 to the negative 8. And I want you to write it out in regular decimal notation. You got it? What did you come up with? 8 times? 1, 2, 3, 4, 5.
Well, 7 times after the decimal.
Okay, like that? 6? 6 zeros? 7 zeros?
7 zeros.
6 zeros? All right, we don't have to fight about it. Let's count it out and see. All right. The nice thing about these is you can always check yourself. You can always check yourself. Whatever you write down, you can count it out again. So let's start with this decimal place, and we'll count it out till we get to just past the 3. 1, 2, 3, 4, 5, 6, 7, 8. That matches here, so this must be right. So that's
It was 32.7 or
3.27.
okay.
Sorry. So the way I would do this problem is, or the way I could count it out if I just saw this, is I would first write those significant digits, because those are going to be important, right? And then you count it out from there. So you can go 1, 2, 3, 4, 5, 6, 7, 8. And however many holes are there, or little slots, you can put your zeros in. 1, 2, and then one more on the other side of the decimal place. And then you could rewrite it to look nice, but that way you're sure to have the right number of pockets every time. So there are some practice problems from this in your book. This is one of those things that I think you gotta, I know it's gonna be new to some people this is not a big deal. Certainly something to work on, but it's also something that we'll be using all the time. So you'll get lots of practice with it just from what we do in class. Like what we do today with some unit conversions. Any questions about that? Okay. All right. Let me show you. I think I'm still logged in Blackboard here. Yeah. So if this works, what you can see here is as I'm doing these notes in class, they should just sort of pop up here. Yeah, so they're there. So everything's ready for you right as it goes. And that's on a different computer, so that works. All right, now I got to figure out how to get back. There we go. Okay, now normally on these Wednesday classes, because it's a long block, we'll work for about an hour and 15 minutes or so, and then we'll take a little break, get a snack. You can go do whatever, take drugs, I don't know, whatever you need to do. And then come back and we'll finish up. Today, I think, yeah, let's do it this way. Let's go back to the lab now, and then we'll take a break after that, and we'll come back and do some unit conversions. That'll be a good thing to do while your drugs are kicking. So if you got your lab stuff, pull that up. I'll pull the instructions back up here, and we can go through that. All right, one thing we want to go through here are these pre-lab questions. So, what are the names of the standard units in the metric system for length, mass, volume, and temperature? Now, before you say anything, these pre-labs are meant to be done kind of as homework on your own with research. So it may be stuff that you don't know the answer to when you first look at it. That's fine. That's why it's pre-lab stuff you do at home. You can look it up. So what is the standard metric unit of length? Close. Meter. Yeah, it's the one without the prefixes. But yeah, meter. And then mass? A volume? Liter. And temperature? I didn't. No, you're going to have to print them out at some point. Okay. For now, you can just write stuff down wherever or just do it later. Did you have a question? What? Meter for length, gram for mass, liter for volume, and degrees C or Kelvin for temperature. We're going to talk about temperature units in the next chapter next week. But degrees C is more common, but Kelvin is used in science. Anybody know what Kelvin is? What the difference is?
The lowest temperature is 0.
Right.
100 is right.
Yeah, in the Kelvin scale, the lowest possible temperature is 0, absolute 0. We'll talk about what that means. In Celsius, 0 is what? What's 0 degrees Celsius? What happens? Freezing temperature of water, right. Freezing temperature of water in Kelvin is 273. We'll get to that next time. But anyway, those are those units. So you can look at these guys. And then this is something that we will talk about when we talk about unit conversions in a little bit. But we can give we've talked about significant figures. There are some types of numbers that have infinite significant figures, as many significant figures as you want. And those are known as exact numbers. Looking at these four quantities, some of them are measured numbers. That means they have a particular number of significant figures. And some of them are exact numbers, which means they have as many significant figures as you want. They're absolutely exact. What do you think is an example of a measured number in those four? Miles. Why?
Because you're not sure, then you have to measure it.
You have to measure it, yeah. Couldn't you just count the miles, like
Yeah.
fingers?
Right.
Good.
What is it?
So then is it a measured number?
Because it has a unit of measurement.
It has a unit of measurement in miles.
It's sort of like so does 100 degrees centigrade.
Sure, so does 100 degrees.
But 5 marbles in front of your face, so we're 12 kids.
So 5 marbles, 12 students, those are different?
I think all of these are measured.
They're all measured?
No, exact numbers. No, except for 100 degrees Celsius.
Anybody else have ideas? What do you think? Everyone's just confused now. It's actually, I mean, those terms are a little bit vague because we're using them in a particular context. So when we talk about a measured number, what we're saying is that something that can take a fractional value. So like the miles, 167 miles. Could you have 167.2 miles? Is that possible?
Yeah.
Sure. Could you have 167.2234 whatever miles? Yes. So it can take a fractional value. So you could have 12 students. Can you have 12.2 students? No. So it can't take a fractional value. It's discrete. And so that's what separates our measured numbers from exact numbers. The 12 students is an exact number, which means it has infinite significant figures. It could be 12, it could be 12.0, it could be 12.00, 0.00000, however many zeros you want, you've got it, because it's an exact number. The 167 miles has how many significant figures? 3, right? Because we don't have any more after the decimal place, even though we could. So a measured number could always possibly have more precision, but an exact number can't. So the 5 marbles, again, cannot take a fractional value. You can't have part of a marble. I mean, I guess you could, but we're assuming in this case probably not. And so that becomes an exact number. That has particular consequences when we do conversions with these units, because we don't have to care about the significant figures with exact numbers. We assume that it just has as many as it needs to. We'll get back to that in a minute. Oh yeah, 100 degrees Celsius. What do you think about that one? Is that measured or exact? Yeah, it's measured because it could have fractionally more or less than what is given. It's a particular amount of precision is given. So how many significant figures are in that number, 100.0 degrees C? 4. Even though there's a bunch of zeros there, they're all significant because that 0 after the decimal place tells you that that is the final uncertain digit. And that means that this number is between 99.9 degrees and 100.1 degrees. All right. So you've got all these measurements that you made. And then here is a portion of a graduated cylinder. I don't think we need to go through this one together. I'd like to see you make those designations yourself, but just as a little bit of practice, let's look at one of them together. Let's look at this bottom one, C. Everybody write down what you think that level should be. And we'll see if we have more agreement than we did in the tricky one with the burette. And everybody got one? Still thinking? All right, what do you think? You want to give it a try? 27.1. All right. We get anything else different? Did we get a different number of significant figures? 25.23. Okay. Any others? All right, well, let's count it out. First thing we do, we look at the scale. So this is between what two large numbers first? Well, first it's between the 20 and the 30, right? So it's definitely 20-something. Okay. So it's 20. We have to then count this out. 1, 2, 3, 4, 5, 6, 7. So it's greater than 27, less than 28. So it's 27 point something. Now, can we do we have any more certain digits, or is our next one going to be a guess? The next one's the guess because we don't have any more lines to compare it against. So how'd you guess that? You said what? So we said 0.1 or 0.3. Yeah, those are all reasonable guesses. It's kind of a thick line, so it's hard to say, but I'd say 27.1, 2, 3, 27 point something. One more digit after that would be fine. Probably it should be less than 27.5 for sure, because you can see that it's below halfway. And then you'll get to do it a couple more times on a meter stick. And you looked at some of these in lab, these smallest units. So you can finish those up and turn this whole thing in on Wednesday, a week from today, at the beginning of class. Shouldn't take you a whole lot of time. There aren't any big things to write about with this one. What?
That's going to be the first, second, and third. Or the whole pack. I didn't print it out.
Yeah. So just print out the report sheets, the pre-lab, and then those questions. You don't have to print out all the instructions and everything. Did that. Other questions about this? Do you feel okay with this now, with this lab and everything? All right. It's a little early, but let's take a break now because it's a good stopping point. We'll come back. We'll talk about unit conversions. And that'll be it for the day. So. Let's start back up in 15 minutes. We'll say 6:45. Right.
Then I said,
Tuesday. Wednesday. Next week. Yeah, it'll be more than more. That's why I'll be my
He said it's not just the same.
do you still put this? Okay, so.
Yes.
I want to see.
First, you have to test. Give it a line. So then the next one's going to be your test, where it goes.
Okay.
And that one.
Okay.
It's the pre-lab for both labs, 1 and 2, and then the actual study for, because we're not going to do and then anyway.
It's the same. Doesn't matter which one. The same.
Oh yeah, you have the older version? Let me take a look at it.
I was looking through the table of contents.
Okay, great. Yeah.
When submitting this one, are we doing it with the partner or?
No, those two will be done individually. So your data will be the same, your numbers will be the same because you did it together in lab, but the answers to the questions should be done.
What numbers are you saying?
The measurements.
Oh, okay, I see what you mean.
With this one, there's no real writing or answering of questions, so you can, those all be the same, really. But in future labs, you'll see it'll ask for calculations.
You know, actually,
You can put it all together, and I can do it all together.
do it back to me when you're there.
Yeah, I'll go okay.
No, I didn't. Okay, so this is the one.
Yeah, so it's the same. The problem numbers will be a little off, but you can just do the problems in here. This stuff doesn't change that much.
Pay a penny for it.
Oh, good. Wow. Like online, or did somebody literally? Okay.
Just pay for the.
Yeah, I got the 11th edition, I'm
Okay.
returning this one.
Okay.
It's ridiculous. They're gonna charge us $300 for a textbook and then put up the subway. I don't understand.
Yeah.
I just don't get priorities.
And then what about a subway? You say?
There's a subway like right down the hall. And
Oh. Yeah.
Took away the cafeteria.
What does that have to do with it?
The subway.
they're gonna
Yeah.
upcharge us on books and then throw in a subway.
Oh, and then a subway. It's actually a totally different. The bookstore is not run by Harper. It's an outside company.
It is?
Yeah, it's Follett's bookstore.
I didn't know that.
Yeah. Same with the cafeterias now too. They got rid of the Harper food service, and it's a different company, which is why there's Subway now.
You know the Timberlake, it's this
Yeah.
thing?
Mm-hmm.
Do you suggest keeping this and going with the 11th edition?
No, you want the one that matches your edition.
Okay.
So bring that one back also, and you can try to pick up one from the 11th edition.
For the back manual?
No, it's the answers to the questions, to the homework questions. So it kind of helps you
Is that all
get
of
through
them?
it.
I know I'm like,
I don't know if it's all of them or just the odd
because
ones.
it's like the odd ones in the textbook.
I think the odd ones, I think it's odd ones in the textbook, and I think this has all of them.
So if I were to get the 11th
This one says the
edition,
other ones too. But it goes through and actually shows you how to do all the problems, which is kind of nice for all the different chapters. But you should also be able to pick up an 11th edition of this.
okay, I'll check on Amazon.
What is all that homework? I think you have on the things, just do it. Just do it.
Right, yeah, just do it. Try to keep up with what we're doing in class. So you can expect the measurement stuff. Today is all we're going to talk about that. So after that, try to get that stuff done, because then next week we're going into the next chapter, talking about
Did
history.
you do when you went to
But-
I'm already like almost done.
the
Yeah, so you'd be
like,
fine.
everything was like within that year? Did you do it like after?
Like
It was like
whatever
6
class-
months of school and 6 months of like on-spot training.
No, your clinicals go with whatever class you're in. Pediatrics, you're gonna use pediatrics. Fundamentals of nursing, you're gonna go with clinicals with every class. And you go to lecture 2 or 3. That I've never heard of. But it's a school in Big Paw, and they have like 3 different tracks for their LPN program. Finishing 12 months, 18 months, or 20 months. We'll go through 1 year.
And did you just take a job like right after your clinicals?
Well, yeah, my family has a home agency, so just
So with mom? Do you see how many residents they will say? Gosh, that's. Man, that's ridiculous. And I bet they're all just coming out like.
most of them just live at home.
Do you do like starting care?
Starting first. No. Is this the pre-lab? What is the pre-lab?
It says pre-lab and then for the lab, it's the study report.
I guess we're going there now, right?
No, today's just lecture.
Just shut that, but the same distance, like this one. Like,
That's what you.
this is it.
Right. Where did you print it out?
I already know that I'm not going to be able to attend the class on September 10th.
Okay.
So should I just go to a lecture on Thursday? Or since we just like talked about like the Google Notes or whatever,
Mm-hmm.
can I just do that?
It's up to you. Yeah. I mean, if we end up having a quiz that day,
I can come in earlier.
you can come and do it on the Tuesday or the Thursday class.
Will you be in your office on Wednesday?
Yeah, but I don't like to give the quizzes outside of
Okay.
class early, but you could come to one of those other classes and take it if you wanted to.
Okay.
Or you can just follow along online with the video. Yeah.
Okay.
Minutes.
Okay,
Yeah.
the questions here that we're supposed to do in the lab. Just once.
Oh, yeah. Yeah, I guess those should go down in the lab. Let's see. If somebody else may do that, we'll see if we can get the information from them. Did anybody? The last part that talked about the smallest measurement that you can take on the graduated cylinder and the ruler, did anybody else get that?
I know I asked about that.
I don't know it offhand, so I just didn't get this one. Somebody has that.
In the 10 milliliter graduated cylinder, that, 0.2.
That's right, yeah, because that one is divided into
And then,
point twos.
The 50 milliliters, like 1.5 or 0.1 to 5, because it was measured out in 5 instead of 10. It's the digits like right in, and then between, like, say like 20 and 30.
I think it was 0.1, I think,
0.1.
right?
Oh yeah, 0.1 or 0.5. Sorry, I can't remember.
What about the big one, like this one is the unit of the thermometer using
I think the thermometers are 0.1.
Thermometer? Oh, it's -20.
I think that's asking for what's the smallest increment that you can measure, which is 0.1. Yeah, like what is the smallest amount? So it'd be 0.1 because there were little, or not 0.1, I think it was 1. It's just 1 degree was where the ticks are. Right?
Thermometer, 1.
It was 1, yeah.
and it would also be 0.1.
Right, yeah.
So if you write those 0.1s, what will be the unit of it? Or like what would be in millimeters?
Centimeters. It was 0.1 centimeters or 1 millimeter. All right, we can get started again. All right, so let's come back and we'll talk a little bit about unit conversions and we'll be done for the evening. I'm going to start with a problem, and then we'll talk about how we would, what kind of things we would need to go about solving this, and we'll go back and get that information. root. All right, so this is the kind of questions that we're going to be dealing with. A patient needs 0.024 grams of a sulfa drug. How many 8 milligram tablets should be given? So what's a sulfa drug? Do you know? Yeah. What was that?
It's like a sodium salt, isn't it?
They sometimes are, but in general, when you talk about sulfa drugs, you're talking about a class of antibiotics. They're not terribly common. I'm trying to think of some of the examples. They're often used in topical creams. A lot of people are allergic to them. It's a common drug allergy. So they're not quite as widely used, and they have pretty specific efficacies. Okay. What's the real common?
Penicillin?
No, that's a penicillins are a different class.
They usually have sulfur in the name.
Right. Anyway, we'll find some. So the question is, here's how much you need for this dose, 0.024 grams, and you have 8 milligram tablets. And the problem with this, then, is that those numbers are really in different forms. One number is in a form of a decimal with a gram unit, and the other one is in milligram units. And so we have to do something called a unit conversion. We have to change the units of one to the other so that we can more closely match them up and figure out what to actually do. And this is the kind of stuff we're going to be doing in this chapter. Now, these types of problems are going to come up over and over again because we always have different ways of measuring things. Sometimes we're going to be in one unit, sometimes we're going to be in another unit. You may know about English versus metric systems, pounds versus kilograms, liters versus gallons. When you're cooking, sometimes you come up with this where something's given in cups, but you only have a tablespoon, so you have to figure out how many tablespoons per cup, and all this kind of thing. In the health fields, as you, I'm sure, know, those of you who have some experience in there, this is incredibly important. Whether you're a pharmacist or a technician or a nurse or a doctor, you have to have a certain facility for moving back and forth between these units, or you could really get somebody in trouble. And part of the nice thing about the health system is that we have multiple people hopefully looking at these things and checking this, but that also kind of assumes that at least somebody in there knows how to do this, and hopefully that somebody is you. When I talk to the nursing faculty about this class and say, you know, what kind of stuff is really the most important, this is the stuff that keeps coming up for them. They say, when people get into nursing school, we do these unit conversions all the time, and they just really need to get that. So focus more on that. So I say, okay, great, we can do that. So we're going to look at this a lot. We're going to do a lot of work with this stuff, and it's going to keep coming up throughout the semester. Does anybody know how you might go about doing a problem like this? Maybe you've done something like this in the past. What kind of steps can you take?
You have to convert them to be on the same scale, right?
Yeah, that's the big part here. So you've got grams on one thing, and you've got milligrams on the other thing. So we need to come up with a general way that we can always apply, that we can always use to convert from one unit to another so that all our units can look the same and we can actually make some comparisons. So the way we do this is by something called identities or equalities. We make an equality where we say how many of one thing are in another thing. So we say if we have 1 gram, how many milligrams is that? Anybody know? 1,000, right. So there are 1,000 milligrams per 1 gram. Now these metric prefixes are going to be important for you to know in this class. And so if you go back to Blackboard while we're talking about this, you'll see that we're pretty clear about this. you need to know the metric prefixes kilo, centi, and milli. All right? So what does the prefix kilo mean?
Kilometers.
Like kilometers or kilograms? How many is that? It's 1,000. So there's 1,000 grams in a kilogram. There's 1,000 meters in a kilometer or kilometer, and so on. Okay. What about centi? What's centi? It's 100, but it's the other direction. So rather than, it's not that there's 100 grams in a centigram. There's 100 centigrams in a gram, or there's 100 centimeters in a meter. And then milli, as we just talked about, is 1,000, but on the small side also. So there's 1,000 milligrams in a gram, or 1,000 milliliters in a liter. So we'll write those back down. Other units, like switching between the metric and English system, you don't need to memorize those. I'll give you those numbers. You just have to know how to use them, and that's what we're going to talk about now. So let's remind ourselves here. Kilo is 1,000. Centi is dividing by 100, so 100 on the small side. So a kilogram is more than a gram, 1,000 grams. But a centigram and milligram, that's smaller than a gram. And that's why I do the 1 over 1,000. So we can write these inequalities. For milli, kilo, and centi. And we'll sometimes use some other prefixes too, and you'll see them in your homework. That's fine, but like I said, you don't have to memorize those. You can look them up if you need to. So like we talked about micrograms or micrometers. That's 1,000 less than milli. When those kinds of things come up, I'll give you those numbers so you don't have to memorize them. These are the kind of identities that we're going to use. Now, are those exact numbers or are those measured numbers? In other words, are there exactly 1,000 milligrams in a gram, or is it 1,000.0 something? It's exact. It's exact. It's a definition. There are exactly 1,000 milligrams in a gram. So then so we've got these identities. How do we use these identities to do the conversion that we want to do? You know? Yeah, we divide or multiply depending on which way we want to go. And it looks like this. We take an identity like this, and we put one over the other one in a fraction. So we say that we can write this as 1 gram per 1,000 milligrams, or 1,000 milligrams per 1 gram. We can always do that because we're saying that those are the same, and therefore they're 1, and we can always multiply by 1, for those of you who have done that sort of thing in math. So we can always make these kinds of fractions between equivalent things. And that, yeah?
I was going to say, can't you just say like that's to the left, right?
Yes, you can do it that way too. That's kind of a quicker, shorter way to do it. The reason I'm going out this way is because when we get to more complicated factors like going between English and metric units, that doesn't work as easily. But within the metric system, absolutely. You just move the decimal places back and forth. Yeah. So in this case, what we would do is set up a multiplication that allows us to figure out how to get from one unit to another. And again, like I said, of course there are shorthand ways to do this. You may have done this a million times, and this seems silly. But when we get into more complicated ones, it's nice to be able to set this up this way. So here's how I'm going to set it up. I'm going to take my first number, 0.024 grams, that was given in the problem. And I want to multiply it by one of these factors to turn it into milligrams. So get rid of the grams and get milligrams. The way I do that is by using a property of multiplication, where if you divide something by itself, it cancels out and becomes 1. So if I multiply this by the second factor that I wrote, we have gram on top, gram on the bottom. If there's no fraction, we assume it's on top. Gram on top, gram on the bottom. Those cancel each other out, and we end up with milligrams. Right? So what we want, we keep on the top, and what we want to get rid of, we put on the bottom. And then we solve that multiplication problem. So what this is telling us is if we multiply 0.024 by 1,000, we will end up with milligrams instead of grams. And multiplying by 1,000 is like moving the decimal place 3 times. So 1, 2, 3. 24 milligrams. So this first 0.024 gram measurement can be converted into, instead, 24 milligrams. Now we have a little bit easier of a problem on our hands, because how many 8 milligram tablets add up to 24 milligrams? 3, right? 8 times 3 is 24. 8 plus 8 plus 8, 24. So this is going to be 3 tablets. But that wasn't so clear until we were able to do that conversion. All right. Good so far? Okay, let's try another one. Whoops. So another common thing that happens in medicine is most medications are dosed in grams or milligrams, something like that. But most people use the English system. So if you're taking a history on a patient or something, and you say, how much do you weigh, they're probably going to tell you in what unit? Pounds. They're probably not going to say kg. So they might if they are from somewhere else. But people around here are probably going to say pounds. And so if you want to know, if you have a dose chart that says so many milligrams per kilogram, and this person just gave you their weight in pounds, well, you got a little math to do there, right? So, yeah, so we got to use another conversion factor. And this one is 2.20 pounds is 1 kilogram. And this is one you don't need to memorize. I'll give you that number if you need it. Is that an exact number, or is that a measurement? What do you think? You say exact? Exact? Anybody say measurement? It's a measurement to you? Why?
Because the unit of measurement pounds, and then also as decimal.
Yeah, the decimal is kind of an important thing here. Remember our definition of exact versus measured. It has to do with, is it possible to have fractional amounts in one direction or the other? So in this case, this is actually a measured amount. If we needed more significant figures, we would go out and find some more numbers on a more complete conversion chart where it was 2.20 something, 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 something. So we just shorten it. We round it and shorten it to make it easier on ourselves. So whenever we're going between the two systems, we're using measured numbers, not exact numbers. And that means we have to pay a little bit closer attention to the significant figures. All right, so let's say somebody comes in who weighs 155 pounds. And we want to know how many kilograms that person weighs. So we want to find a factor that allows us to do this multiplication as we did before. We want to multiply this by some kind of a factor that allows us to cancel out the pounds and end up with kilograms. So if you can set up that fraction where you can cancel out what you need to cancel out and end up with what you want to end up with, then all you have to do is plug the numbers in from the identity. So if it's 2.20 pounds per kilogram, we plug in those numbers. We divide. Does somebody have a calculator? Try that one out. What do you got?
You want it, 155 divided by
Yep.
7.
So this setup this way means that to get that number, we have to divide 155 by 2.2, because the 155 is on top, the 2.2 is on the bottom. We have to do that division. We end up with 70.4, and that's our mass in kilograms.
If I ever wanted to round it, like the digit, like it was 7.45,
Mhm.
I just round to 7.5.
It depends on the significant figures that you need to report. And like I said, we're not going to go through all those rules. So a general rule of thumb is keep about as many decimal places or significant figures fairly consistent throughout the problem. There are specific rules for that. We're not going to go through them in this class. So just don't go crazy with it. If it's a weird calculation and it comes out with a bunch of decimal places on your calculator, there's no need to write those all down. Pick a couple. And somebody whistling? Is that a phone? Just pick a few and put it in there. That's fine. It's a phone, right? Okay. It's scaring me a little bit. All right. Okay, let's try some more. These can encompass all kinds of different situations and all kinds of different types of units. Let's try some different ones. Then we have to find some conversion factors here. But this one says a dialysis unit requires 75,000 milliliters of distilled water required. But you go to the grocery store, or your distilled water supplier, I suppose, and you see that the distilled water is probably in what kind of a container? Probably in a gallon, like a gallon jug, right? Yeah, but ounces, it's probably not going to be in liters or milliliters. So you got these gallon jugs. So how many gallons do we need to get 75,000 milliliters? Well, we need some help. We can't quite solve this yet, because we need to know how many gallons, or how many milliliters are in a gallon, or how many gallons are in a milliliter. That's not a common conversion factor. And let's say we can't find that one. So here's what we get instead. If I can find one. All right, there's a chart, I think, in the book here somewhere. Here are some useful conversions. Okay, so I see in this useful conversions table in the back of the book, 1 quart is 946 milliliters. So that's the best we can do. I don't have any gallon conversions, but I've got a quart conversion, so maybe we can work with that. How many quarts are in a gallon? 4. So we've got 4 quarts per gallon. Okay. Well, you might be right. We'll probably ahead a little bit. So in this case, it's not quite as simple as what we were doing before, because we don't just have one conversion to do. We actually have two. We can't go straight from milliliters to gallons because we don't have a conversion from milliliters to gallons. So we have to go milliliters to quarts because we got that one, and then quarts to gallons because we got that one. The neat thing about this method that we've been looking at is you can actually set all of this up and do it at the same time. So it looks like this. We can take our 75,000 milliliters of distilled water, and we can multiply it by some factor that gets rid of our milliliters. Yeah, so we're going to put our milliliters on the bottom and quart on the top from this first conversion factor. Now, how did I know to put milliliters on the bottom? Because I want to cancel it with this milliliters here. So I get 946 down here and 1 up there. Milliliters cancel with milliliters, and I'm left with quarts. But I don't want quarts. I want gallons. Gallons is what the question is asking for. So we have to do it again. This time, we're going to get rid of our quart, and we're going to turn it into a gallon using the other conversion factor. 4 quarts into 1 gallon. So to complete this problem then, we take 75,000, divide it by 946, because that's on the bottom, and then divide by 4, because that's also on the bottom. We've canceled milliliters, we've canceled quarts, we're left with gallons, and what does that come out to? Anybody punch that out? Suppose I have a calculator here. What did you say? 19.8? Let me see if I get it. Yep, 19.8. That's what I get to. $19.8 gallons. All right, so we're going to go to the store, buy 20 gallons, and we'll have just enough and a little bit extra for our dialysis machine. All right, want to try one on your own? Maybe with friends?
So did you divide the 75,000 by 946 and then convert that into
Right. So you can do this because multiplication is associative. You can do this. You can go 75,000 divided by 946 equals, and then that divided by 4, or you can just put it in one big string. Just keep hitting the divide sign. All right, let's try another one.
I would have done it. I would have just done 946 times 4 and then divided that by 7.
Yes. Did you get the same thing? Yeah.
Okay.
Yeah, it doesn't matter what order you do it all in. I should say, I'm showing you a very specific way to do these conversions. That doesn't mean that the way that you already do them is wrong. You may have learned it and done it well, and that's great. Stick with what works for you. I'm just introducing a method that works for me and that might work for you if you're new to this or if you've struggled with this before. But yeah, if you've already got your system and it works, stick with your system. Okay, this is another medication. So we're going to look now at a bacterial infection that requires 4 tablets of amoxicillin per day. That's pretty standard. And each tablet is going to be 250 milligrams But here's the question. Oh. And we're going to take this for 10 days. All right, 10 days of antibiotics, 4 tablets a day, 250 milligrams per tablet. How many ounces total were taken? How many ounces of amoxicillin were taken? And I got to give you one more number for that. And I know that. And the number I'm going to give you is the one that we used before. And then you need one more. How many ounces are in a pound? 16. 16 ounces in 1 pound. All right. So on this problem, I want you to, you can try it on your own if you want, but work together. Talk to each other. Either try it on your own and then talk about how you did it, see if your answers compare, or just talk about it as you're working through it. And see if you can figure out how many total ounces were taken after 10 days of this 4 tablet a day, 250 milligram per tablet amoxicillin. You can set it up the way I had it set up before, or you can do it your own way. Because that's how we are going to be able to convert milligrams to ounces. So there's no milligram ounce conversion. We've got milligrams, kilograms, pound, ounce. So it's a few steps there. So this one gets a little trickier. Yeah. Help each other out on this one. I'm not just going to tell you how to do it.
So just out of curiosity, the
Yeah.
4 tablets, is that for like what we have to multiply our answer by when we convert the 250 milligrams into the ounces? Or do we just ignore the 4 tablets a day? Because we already know the patient's getting a total number of 10 tablets.
No, for 10.
For
10 days,
right,
4 tablets a day.
40 tablets.
So 40 tablets. So it's probably easier to go that way. Get a total mass in milligrams first, and then convert it to ounces. If you can. No, you're shaking your head?
No.
Not going well? Everybody's so quiet. Everybody's so quiet. Maybe you can figure it out together.
There are decimals in this.
I don't know. Probably. Does that change it?
No, it is.
All right, where would you say is the sticking point? The beginning. Okay. All right, that's fine. One thing I would say here, so there is a way you can kind of do this as one big giant string of things, but I think it's probably easier to think about this a little bit more logically and come up with a total mass first. So the main part of the conversion thing is converting milligrams to ounces, right? That's kind of the point of the problem. But then you've got all this other stuff thrown in about tablets and days. So if you can just get one big number of milligrams first, then you can start setting up to convert that one. So how'd you get that big number of milligrams first? That total dose over the 10 days is going to be what? How'd you get 10,000?
40 times 250. We multiply that by 250.
Yeah, so you got 250 per tablet. You're doing 4 of those a day, so that's 250 times 4. And then 10 days, so you're multiplying it by 10 again, and that comes out to about, what did you say, 10,000? All right, so let's use that as our starting point. Now that we've got 10,000 milligrams. Now it would be great if we just had one little conversion factor we could multiply by and get milligrams to ounces, but we don't have that. So the plan has to go through what we do have. We have kilograms to pounds, and we have pounds to ounces. So we have to go, I mean, there's a couple shortcuts here, but I'm going to do it the full way here. We have to go milligrams to grams to kilograms. We can do that from the prefixes that we just learned. Then we can go kilograms to pounds using our first number here. And then we can go pounds to ounces using our second number here. In each case, we're going to set up a conversion to cancel out that first one and end up with the second one. So we start with milligrams, then we want to cancel milligrams to get grams, cancel grams to get kilograms, cancel kilograms to get pounds, cancel pounds to get ounces. So there's going to be a few little fractions there. See with those, with that started now, see if you can set that up and continue.
I'm separate by the kilograms to pounds. Do you
Okay.
the 0.01 and multiply that by 2.20 or divide it?
Well, you want to get rid of kilograms and end up with pounds, right?
Right,
So the pounds are going to go on top,
right,
kilograms go on the bottom.
right, and that cancels the kilograms.
Yeah. So then we just use the equality. The 1 goes with the kilograms, the 2.2 goes with the pounds. So that ends up on top. You got it? Okay. I don't know the answer, so I can't confirm or deny it yet. You got it? Okay. Well, that's good. Are you still working? Do it another couple minutes. Finish it up. If you're done, compare answers with people around you, see what kind of numbers you got. You can get up and walk around too, you don't have to stay there in your seat.
You took the 0.0.
No? Maybe? A little? Not at all? Okay. All right, let me show you how I would set this up. So when I set this thing up, again, if you focus on the units, you can plug the numbers in later, and you're more likely to get it right. So in this case, I'm going to put my milligrams here top to bottom so they cancel and end up with grams. My next one, I'm going to want the milligrams, or I'm going to want the grams on the bottom and whatever I want next on the top, in this case, kilograms. Then kilograms to pounds. Then pounds to ounces, and that should be good, right? So now it's a matter of filling in those numbers and doing the math so that it makes sense. We know there's 1,000 milligrams in a gram, 1,000 grams in a kilogram, 2.2 pounds in a kilogram, and 16 ounces in a pound. by focusing on the units, you're less likely to make the biggest or the most common mistake here, which is just flipping things the wrong way. If you always think about your units canceling top to bottom, there's less chance that you'll flip one upside down. If you look at the numbers, there's a greater chance that you'll mess that up. So that's why I put the units in first and then add the numbers later. When I punch this in, I'm going to take 10,000 divided by 1,000 divided by 1,000 again. Then multiply by 2.2, multiply by 16. And what do you get? That doesn't seem right. Oh, yeah. Sorry, I got confused here. 0. What did you say it was? 52 ounces. All right. So think about how we went about doing that problem. We first got rid of the dose stuff and made just one big massive amount that we had to convert, and then we did the conversion. If you really like setting these things up, and I know you do because it's fun, what you can actually do is bundle that first part in there as well. So you can add a couple conversion factors, and you can actually start all the way back with that 250 milligrams per one tablet. We can multiply by 4 tablets per day. So now we're converting milligrams per tablet to milligrams per day. And then we can multiply by, there's no line for that one because it's just 10 days. So this is kind of a way of doing this and getting that same number that we came up with originally. All right. Maybe okay with this, at least a little bit at the beginning? This is the kind of thing that takes practice, absolutely takes practice. And you know, there's a whole chapter full of practice problems in there for you to look at over this week. So we'll have our, go ahead.
Yeah, I'm still stuck on the
All right, let me check the calculation here. What, did you get something different?
No, I just
Okay. Do you see how we set up this conversion? All right. So now what I'm going to do is I'm just going to put it in the calculator. 10,000 divided by 1,000 divided by 1,000 because that's on the bottom times 2.20 times 16. And that's it. Yeah.
So do you always divide the numbers on the bottom?
Yeah.
Multiply them?
Yes.
Okay, that's what
Oh, okay. Good. I'm sorry. I should have said that more
How do you
clearly.
know when you're supposed to divide and when you're multiply?
You got it. That's how you know.
Okay.
So the numbers on top you multiply, the numbers on the bottom you divide.
Got it.
Sorry, I should have made that clear. Okay, well there's lots of practice for this. The last part of this then is talking about one more quantity. What? Did you say oh no? Okay. That was a tough one, yeah, absolutely. So now we'll throw something else in there called density. What is density? How would you define density? You've probably heard this word before, right? But you maybe haven't thought about what it really means.
Something to do without gravity?
Something about gravity?
Something without gravity?
Something without gravity?
Something else?
Well, mass actually is without gravity. So grams is without gravity. Anybody want to talk about density? What do you think? Yeah.
The mass and volume of any object that you can measure.
It's the mass and volume? Okay. So it's the amount of mass per volume, we would say, right?
Right.
Yeah. And what's another way we can word that? Anybody? How do you think about density? And I think that's a perfect definition. It's the amount of mass per volume, or another way we could word this is the amount of stuff in a given amount of space. Right? The amount of matter that takes up a certain amount of space. So something is more dense than something else. How would that manifest itself? How could you determine that something is more dense than something else? How would it act, or what?
Weight.
Weight? So what would weigh more? So is everything that weighs more than something else more dense than that other thing? What is the standard there? Or how can you better describe that? Have you ever thought about it in terms of body tissue? Certain types of things in your body are more dense than other things. Like muscle is more dense than fat, probably. Yeah, I think that's true. So what does that mean?
There's more.
It weighs more per the same amount of space. So if you have a cubic centimeter, if you imagine a cube that's 1 centimeter on each side of muscle, that cubic centimeter is going to weigh more than a similarly sized cubic centimeter of fat, because the muscle is more dense. And that's true in general. So the unit that we use for density is grams per milliliter. All of the other conversion stuff, all the other units we've looked at so far, just have one unit after them. So many grams, so many milliliters, so many ounces. This is a compound unit where you have grams per milliliter. So how much mass, how many grams, how much stuff is in a milliliter. Another way you'll sometimes see this written is a gram per cubic centimeter, because in fact, a milliliter is a cubic centimeter. If you imagine a cube that is 1 centimeter on every side, that volume is also 1 milliliter. So you'll see density as grams per milliliter or grams per cubic centimeter. Does anybody know what the standard density is, the density of water? And take a guess? It's a pretty common number.
7.
Close.
10.
Less close.
5.
All right, I'll just tell you. It's 1. So density of water is 1 gram per cubic centimeter or per milliliter. What that means is that 1 milliliter of water, remember we used graduated cylinders on Monday, you can measure out 1 milliliter of water should weigh exactly 1 gram. Well, close to 1 gram, depending, it varies a little with temperature, but about 1 gram.
So is that always the case? Milliliters is equals
Yes,
to grams?
cubics is equal to cubic centimeters.
Cubic. Okay.
Now, in water, it is true that you can either measure water by volume or by mass, because 1 gram is 1 cubic centimeter. But other substances have different densities, and therefore are going to be a little bit different. And that's what we're going to use now. So something that is more dense than water, what do you think might be more dense than water? An ice cube? How do you know it's more dense than water? Because of what? It freezes? Okay. So if you put an ice cube in water, does it go below the water or above the water?
Sometimes. Depends on the temperature of the water.
Really?
Yeah. When I filled this up, all my ice stuck at the bottom until I filled it up with water. And then it's still stuck at the bottom.
Was that because it was stuck to the bottom or because it was sinking?
I don't know.
I'm guessing stuck to the bottom because I think ice always floats. Maybe not. Maybe you have special ice.
No, I'll take a picture next time.
Okay.
When I first fill a cup up with ice
Yeah.
and then put water on it, it sometimes sits at the bottom until it like finally rises.
Because
Until,
it's
like,
stuck.
Because it's stuck to the sides, probably, right? Maybe. Yeah. So if you filled it up with water first, right? Good point. And then you put the ice in. Do you think it would go to the bottom? I suppose that's true. You have a finite amount of space. Well, actually, in general, ice is slightly less dense than water, which is why it usually floats. Like when lakes freeze in the winter, the ice doesn't just sink to the bottom, right? It kind of floats on top. So ice is a little bit less dense, and that's actually really unusual. Almost every other substance, when it freezes, it becomes more dense. The freezing action, we'll talk about this in a later chapter, the freezing action brings the molecules closer together and it becomes more dense. In water, it's the opposite. Water traps space inside it and becomes less dense. So let me pull up this table of some densities. Whoops, I forgot to get it started here. So I'll show you some of these pictures. Oh, I have the old version. Okay, because they don't have a new version of the thing online yet. That's okay. It's probably not that different. Yep, there it is. Same picture. So I'm just going to grab some of these numbers with the picture here. All right, so you see in this picture, you got some water and then some stuff in it. And depending on the density of the stuff, you can see where it actually stays in the water. So the cork has a much, much lower density than water, 0.26 grams per milliliter instead of 1. So it floats way up at the top with a bunch of it actually outside of the water. Ice has only slightly lower density than water. So it's in the water with just a little tip peeking out on top. Aluminum and lead both have higher densities than water, so they sink right down to the bottom. And density can apply to liquids and gases, and solids. I mean, all states of matter can have different densities. So you've got some different solids that go all the way from very, very light, like cork, to very, very heavy, like lead. Some liquids, and some gases. Now, one thing that gets confused a little bit with density is sometimes viscosity. So something that is very dense does not, or is not very dense, does not really determine how it will flow. So commonly when I ask people about oil, like cooking oils, oil is very viscous, right? It flows very slowly. But it's actually less dense than water. Olive oil, 0.92. So what that means is when you pour oil into water, the oil will actually sit on top. Oil is less dense. Right? Yeah. Right. And you can see these bodily fluids are slightly more dense than water because they are water with some other stuff dissolved in. As you put that other stuff in the water, you make things heavier. All right, so we can do some of these calculations with density now that we know that it is, I'll remind you again, grams per milliliter. So the way that you would measure density, and if we had lab next week, we would do this in lab, is by taking a known volume, measuring its mass, or taking a known mass and measuring its volume, and then dividing the two. So, example, let's take 2 teaspoons of cough syrup. Doesn't say what kind of cough syrup. Anybody ever taken cough syrup before? Coughing syrup. Take a bunch of it, you can hallucinate. If it has a density of 1.20 grams per milliliter. Okay. We can answer questions like this. What is the mass of the cough syrup? So we need one more piece of information for this. There are 5 milliliters in a teaspoon. So this looks a little bit fancy because of this density, but we can really treat it like just another conversion problem. We can convert from teaspoons to milliliters, and then here's where we can do something new. We can convert from milliliters to grams using the density. So all of our previous conversions in the previous parts have been the same type of measurement, length to length to length, or weight to weight to weight, not actually changing what we're measuring. But when we have a quantity like density that relates mass and volume to each other, we can now switch between volume measurements, teaspoons and milliliters, and mass measurements of grams. The nice thing is, we don't have to do this problem in a different way. We don't have to do anything fancy. We can set it up exactly as we set up the other problems. We're just using now a different quantity. So here's what it looks like. We take our 2 teaspoons and we want to convert them to milliliters. How do we do that?
There's 5 milliliters in 1 teaspoon.
Yeah.
So you put the 1 at the bottom and the 5 at the top.
Right. So we can set it up just like this, where we cancel out the teaspoons and we're left with milliliters. Now, we don't actually want milliliters at the end, right? We want grams. So to convert from milliliters to grams, what do we need to use?
Wait, you want to convert milliliters to grams?
Yeah.
Some grams over.
Yeah, we need some quantity here that will allow us to cancel milliliters and instead end up with grams. What quantity is that? The density. Is that what you said? Oh. Yeah. Right, it sounded like density. But this is the density. The density tells us the relationship between grams and milliliters. Even though we write it like this so it stays nicely in line with our writing, what we really mean is that there are 1.20 grams in every 1 milliliter. So it's really a conversion factor. It was given in the problem. Any material is going to have a different density, so that's going to have to be given to you. But we can plug that in here now, 1.2 grams per milliliter. And so we can find that the mass of the cough syrup is 12 grams.
Do we have to pick it up? Oh, because I put it over 10. But it would just be more.
Yeah, it would be over 1 milliliter. Otherwise, you're going to be off by a factor of 10. So that's how we can use the density. Now, the important thing here, the thing that I really want you to look at, is that this problem is no different from the previous stuff. We're still setting up a string of multiplication that allows us to cancel certain units and be left with others. The only difference here is that one of those is a density that relates grams to milliliters rather than an identity that relates two of the same kinds of quantities to each other. All right, let's try another one. All right, you got a glucose solution in an intravenous bottle. And it has a density of 1.15 grams per milliliter. It's a little bit more than water because all that sugar that's dissolved in there. What is the mass of 0.500 liters of this glucose solution? So you're given something in liters, and we want to know mass. But the only way we can get to mass is using that density, so there might have to be another step there. So think about this, talk about it, see what you come up with. Anybody feeling good about this one? Maybe a little? Yeah? Okay, good. You got it. Talk to people around you and see, or if you're just stuck, see what other people are doing. All right, let's throw out some numbers. Anybody got one? Doesn't have to be right. Let's just see. Let's see how it goes. No? Got nothing. 765. Can we get something else? Anybody get one of these numbers? Yeah. You got 575? Okay, thanks. Anybody else? All right, well, let's set this thing up in the same way. What's the missing piece here? Right. So our density, we have milliliters, but our solution is given in liters. So we've got an extra little step to deal with there. We'll start with our volume, our 0.500 liters. And then we want to convert that to milliliters. So we want liters on the bottom and milliliters on top. And what is that conversion? Right. 1,000 milliliters is in 1 liter. Okay, so that's good. That gets our liters canceled. So then our next thing is now we have our milliliters, we can go to grams. So milliliters on the bottom, grams on the top. And that's the density. So 1.15 divided by 1 milliliter. So it's going to be 0.500 times 1,000, which is 500, times 1.15, which should be 575. So all these kinds of problems can be set up and solved in this way. And we'll keep doing lots of them like this. It'll come up in the next chapter when we talk about energy. We have to convert between calories and joules. It'll come up later when we're dealing with gases, when we talk about moles and other quantities for chemical reactions. We will keep doing this again and again. So it's a great thing to focus on for now, for this week, to really make sure that you get a sense of how this works. And certainly come see me if you need some help. All right. Questions about that problem or about this? All right. Well, let's stop there. We'll end a little early tonight. So no class Monday. That means next Wednesday we're back here. We'll have our first quiz. And we'll do some conversions on Wednesday for our first quiz. No, but I'll give you all the numbers you need, so it's basically up to you. So it'll be next Wednesday, the beginning of class, we'll just have a quick quiz, and then we'll go from there. It'll be a good way of moving. It'll be very closely related to homework problems and stuff we're doing today. Shouldn't be anything too crazy. Also, please bring your labs from this week. And since we'll get more information about what to do about that too.